Okay, so last time we talked about flats, right, which are basically linear subspaces that you can think of as generalizing things like points, lines, planes, and so on. And flats are pretty important. They show up in a lot of different applications and contexts. But one problem with flats, or a limitation, is that they are all infinite in extent. And many of the things that we're going to care about are going to be finite types of shapes. And one interesting collection of shapes, which we're going to start out with today, are simplices, right? So a simplex is kind of like a generalization of a triangle. You can think of it as being something like a line segment or a tetrahedra or a point. And so they sort of exist in some higher dimensional setting, right? So, yeah. So the simplest example of a simplex is a line segment, right? So we'll start with this idea. Let me get another pen. This one's kind of dead. Basic idea, and we're going to start out working in affine space and move on to kind of a projective version of this whole story later, probably not in this lecture, is we have a pair of points, call them P0 and P1, and a line segment is basically this collection of all of these points which are swept out between the 2 points, right? So formally, we say that this line segment here is the set of all convex combinations of these pair of points, right? So the way to think about this is that we're going to have some parameter t, which we're going to imagine interpolates between P0 and P1. So as we vary t from, say, 0, it starts at P0, and as we go to 1, it ends up at P1. So the idea is this is the set of all points, 1 minus t times P0 plus t times P1, right, for t in the interval 0, 1. All right? So what this should kind of geometrically tell you is that if you pick, say, like t equals 0.5, you'll end up like halfway between the 2 points. If you got 0.25, you'll end up over there. And you can imagine kind of like sliding it to, sort of scrub back and forth between the 2 of them. Similarly, we have triangles, right, where a triangle is again determined by 3 different vertices. We'll reuse the same names. Right? And it's defined in the same way, except you have now 2 parameters that generate the triangle instead of just 1. So the basic idea is we're going to have this s times P0 plus t times P1 plus 1 minus s minus t times P2 for st in the interval 0, 1, and with this additional constraint that s plus t is less than 1, or less than or equal to 1. All right. So we can generalize this idea a bit, sort of iterating into higher dimensions, right? So I think I'm good for space, but I'm going to erase a little bit here just to make sure that the camera can do this. So by the way, for the people who are just joining us in this new lecture, the lectures are video recorded, and they're on the CIE webpage. But in order to do this, I have to use the camera here, and it only captures like up to this chunk of the board, so the rest of it's like not visible. So we can make kind of a table. So we'll have here 3 columns. We'll have the number of points, dimension, and sort of a name, which is just like an arbitrary kind of convention. So if we have 1 point, you have a 0-dimensional simplex, and it's just called a point, right? So that's easy enough. If If you have 2 points, you get a one-dimensional segment. This is just a line segment. 3 points, you get a two-dimensional shape. And it's a triangle. 4 points, you get a three-dimensional shape. It's called a tetrahedra. And this can just iterate off until you get up to d plus 1 points, d-dimensional shape, and the result is called a d-simplex. So, okay, straightforward. So how do we define a d-simplex? Well, you just kind of iterate on this type of pattern here. So the general concept of a d-simplex, right? And we're going to put some constraints on this in order to make this work. So we'll just say, OK, so we'll say given d plus 1 affinely independent points. And remember affine independence from last time, right? Finally independent points. And we're going to work in affine space for now. Well, we'll make it an AN, right? Because D could actually be independent from N, right? So we're not going to require it for now. A D-simplex S subset. And let's call the points V, right? We'll give them a name. Subset of AN is the set S, which is going to be equal to something called the convex hull of these points. All right, so it's the convex hull of V, which is basically the set of all convex combinations of the points. And so these are defined by taking weighted linear combinations of the basis points. So we'll say it's A1, V1, or A0, V0, plus A1, V1, plus AD, VD, subject to the constraint that 0 is less than or equal to AI. So all these guys are non-negative. And that the sum of all these AIs equals 1. All right. So you can see that in the particular case of, D equal 1, then you get the definition of a line segment. When D is equal to 2, you get a triangle, and so on, right? You have to do a little bit of arithmetic, though, because we have one extra parameter here. But there's also this equation here, which allows us to kill any particular variable by basically solving for it. So for example, if we had 2 parameters, we have, say, like A0 plus A1 equals 1. That implies that A1 is equal to 1 minus A0. And so we can basically just stick the weights in there. Right? So that's the idea, right? So this operator here, right, this is the convex hull. And we'll return to this in a moment. But for now, let's spend some more time talking about simplices. So simplices are great. There's lots of things we can use them for. I mean, in computer graphics, most drawing operations turn into just transformations of simplices or projections of them onto a screen. A lot of operations in geometry will hinge upon decomposing things into simplices. And later on, we'll see that like most geometric structures, will have some kind of simplicial decomposition, that we'll make use of. I'll explain these words in a moment, right? But one thing that we can do with just a simplex all by itself is we can calculate some different measures from it. So for example, for like a line segment, we could compute its length. For like a tetrahedra, we could compute the volume. A triangle, we could calculate the area. And we'd like to have some kind of general formula for doing this in any dimension. So this brings us to the concept of the measure of a simplex, which is like a generalization of volume, right? Or it's basically the same idea, right? Just dimension independent. And the way we do this is using a sort of standard kind of result from linear algebra, right? So you may recall, in 2D or 3D space, right? If you have, say, and I'll just draw this in a plane right now, right, to show you how this picture works. So in a plane, imagine I have a pair of vectors here. We'll call them u and v, right? Then I can sweep out this this parallelogram here, right? Where this would basically be u shifted, this is v shifted, and then the main diagonal here is u plus v. So I have this parallelogram. I'll call it P, right? Then the area of that parallelogram is equal to the absolute value of the determinant of a matrix spanned by the column vectors u and v, right? So that means that basically like the area of this structure is just the determinant. And so if I had a triangle that was swept out by u and v, I just draw a diagonal around there, then call this triangle delta, right? Then the area of that triangle, delta, is going to be 1/2 of the determinant, or 1/2 of the area of that parallelogram, which is going to be 1/2 of the absolute value of the determinant of u and v. Now there's another way I could calculate this determinant too. I could think of it in terms of this angle here, theta, right? So if I wanted to think about this trigonometrically, then this determinant here, right, which let's just call it d, right? Actually, I'm reusing that variable. Let's call it uppercase d, right? This uppercase d here, via sort of standard trigonometry angle chasing, right? You can verify this yourself, is going to be proportional to the lengths of u times the lengths of v times the sine of that angle, theta, right? So in this way, we have this basic operation, determinant, right? And we can use it to calculate areas in 2D. And in higher dimensions, it generalizes to computing volumes of these parallelepipeds, which are spanned by these vectors swept out. So from this idea, we can define something for any given simplex, which is going to be the measure of the simplex. So, so given a simplex, d simplex, let's call it S, which is equal to the convex hull of a vertex at V contained in d-dimensional affine space. The measure of S, and we're going to just define it here, right, is 1 over d factorial times the determinant of a matrix whose columns are just the vectors in V. So we'll just write this as, say, V0, V1, etc., to Vn. But remember, we have to subtract off the V0 at each point, right? So this should actually be, I should actually fix this right here. It should be V1 minus V0, V2 minus V0. It's actually Vd minus V0, right? So that's the correct way to write that. Right, so we should think of these as just being column vectors that are swept out. So the idea is that we basically take V0 as the base point for this simplex. We move it to the origin. And then we basically calculate the volume of that parallelepiped. But because it's in, it's a parallelepiped, not a simplex, we have to divide by d factorial because we're basically, dissecting it into, d factorial different pieces. So in 3D, it would be, 1 over 6 times this, in 4D, it would be like 1 over 24, and so on, right? So that's kind of the general pattern, right? So that's the basic intuition for volumes and measures and areas. Now, for any simplex, it also determines a coordinate system in affine space, too. So if we have a full d-dimensional simplex, we can use it to parameterize any point in affine space in terms of the vertices of the simplex. And that's because we have this expansion right here, right, which basically generates the points inside the simplex. So imagine, I have, like, say, a triangle and a plane. Right? I pick a point x inside the triangle, and these are my points P0, P1, P2. Then there should be some coefficients, A0, A1, A2, that determine x, right? So if I write this out in a set of constraints, right, or as a set of equations, I have the equation A0, P0. Let me draw a box around that so it's clear that there's something else going on here. P1, A2, P2. This should be equal to x. But then I also have this additional constraint that all these a's sum to 1, which is what makes this well determined. So I have this a0 plus a1 plus a2 equals 1, right? So this would be the system that I would want to solve. So if I wanted to figure out the coefficients are the coordinates of x, written in terms of these coefficients here, right? I just have to solve for these a's in terms of x. So I can write this out as a matrix, right? So I'm going to introduce a new matrix. We're going to call this guy P, right? Who will basically have P0, P1, P2. And I'm just going to put a 1 at the bottom here, right, to simplify this a bit. So you can actually imagine that this is kind of the same thing as if I lifted these guys into projective space, right? Start working there. I'll create a new vector, capital X, which is going to just be x with a 1 stacked on it. And then I'll also create a vector A, which is just going to be a column vector. Or let's see, should be row vector, right? A0, A1, A2, right? And so with these three vectors, this system then becomes P, A equals x, right? And then just solve for A given x, right? So this will basically just be coordinates of x means solve this for A. All right, that's how we get the coordinates of x in the triangle.
I have a question, sorry. The
right.
P0, P1, P2?
These are column vectors, right? So they're just points in the affine plane, which are two vectors. So they're a 2D column vector. All right, and I'm just stacking them here. So this is sort of like matrix notation. So I have a P0, P1, P2.
So
right?
That's a 3x3 matrix then?
Yeah, it's a 3x3 matrix. This is 1x3, or no, 3x1, and then this is a 1x3, right?
Okay.
So if I take this first row times this column, yeah, so actually it might be, this needs to be transposed, I don't know, whatever, yeah.
So it should actually be a 3x1?
Yeah, exactly. I mean, it's basically, I just want that if I multiply it by A, right, then I should get P0 times A plus, or A0, A1 times P1, A2 times P2. So I'm just filling in this part of this equation right here. And then this equation right here is just the bottom part of this P.
Oh, okay.
All right, that's all that's going on. All right, now you can also interpret it projectively too, right? But we're not going to do this in today's lecture. We're going to stick to affine coordinates for now. We'll come back and do this all over from a perspective, projective kind of point of view. But that will be another time, right? Not today's lecture. So, OK, we have this equation, right? We want to solve it. All right, well, there's many ways you can solve linear equations. You could use Gaussian elimination. But one kind of geometrically intuitive point of view is to use Cramer's rule, right? So how many people here remember Cramer's rule from linear algebra? All right, so you remember this concept called like a cofactor expansion or cofactor matrix? All right, have you ever seen this before? Right, so this is a, OK. So Cramer's rule, right? I'm going to erase this stuff. Right, so the basic idea behind Cramer's rule is that it's a way to solve a linear system by just calculating a huge number of determinants. So it's essentially, like, you can actually view this as really like the secret origin of where determinants came from. So, going back far enough, right, determinants were kind of invented sort of in parallel or independent from Gaussian elimination. And they're kind of a product of like an attempt to come up with a closed form solution for a linear system. So it's basically like some function where you just dump in the coefficients of your matrix and then out pops like the exact equation, right? So you could think of this as like an algorithm-free kind of calculation, right? It turns out to be not a very efficient way to solve linear systems because the size of these things, if you expand them out naively, is pretty horrible, right? But Cramer's rule is basically one sort of brutal way to solve linear systems. And for low-dimensional systems, like this sort of 3x3 matrix here, it's totally adequate. The basic idea, though, is that if I have some matrix here, M0, 0, 0, 1, 0, 2, 0, 2, 2, 0, 2, 1, and 2, 2, and I want to compute the inverse of this matrix, Well, Kramer's rule tells me that I can calculate the inverse of this matrix, or the solution to it, by computing cofactors, right? So the cofactor for this matrix in this coordinate here is basically m00 times the determinant of this minor, right? So it's going to be times m11, m12 minus m12, m21, and so on, right? I mean, this becomes pretty messy if you fill it all in, right? But the idea is you basically go say, well, OK, for this entry, you take this m00, you multiply it by -1, compute the cofactor for this thing, multiply it out, and you just do that and fill in all of the entries of this matrix. And then you divide by 1 over the determinant of this matrix over here, right? So that's the rule for doing it, OK? So if we apply it to this x here, though, and we choose to invert it, right, then what we'll see is that basically these cofactors that we get will show up in the form of, or there basically will be like this weight m00 times p, right? And then a 1 here at the bottom, right? So you can think of this as being like the first column. The next one's going to have an m01 or whatever, which will basically be the components of p1, and then the components of p2 times these cofactors, right, which are expanded out. So if we do it in this way, we'll see that this will end up being, when we solve it using Kramer's rule, the area of this triangle divided by the area of the whole triangle, the area of this triangle divided by the area of the whole triangle, and the area of this triangle, right? So if we solve for x, right, or if we solve for a given x using Kramer's rule, right, skipping a couple of steps here, and you should verify this on your own. Just go through and just do the calculation, right? We'll see that a0, right, which is the weight on p0, turns out to be the area of this triangle, right? We'll just say it's the measure of the triangle x p0, or no, x p1 p2 divided by the measure of the triangle p0 p1 p2. And similarly, a1 will be the measure of the triangle x p0 p1 divided by the triangle p0 p1 p2. And a2 will be the measure of, I'm going to draw like some lines here to kind of split this up and make it a little cleaner. The measure of the triangle x p0 p1 divided by the triangle p0 p1 p2. OK, so those are basically the coordinates that you end up with, right, for x, right? So you can solve for these a's explicitly using this formula. And what this basically shows is that each of these a's are going to be proportional to ratios of volumes. And so in this sense, this coordinate system is sometimes called areal coordinates when you use them in 2D, or it's sometimes called barycentric coordinates. Right? So barycentric coordinates are a fairly convenient way to talk about points on triangles. In computer graphics, they show up a lot. So if you're like texture mapping a triangle or rendering points on there, and you want to interpolate between different weights which are on the vertices, then these barycentric coordinates are a pretty convenient way to do so. All right? And of course, you can generalize this to higher dimensions, right, where you basically take a point, you split the simplex into d plus 1 sub-simplices, and then you just calculate the measures of each of those, or the ratios of the measures to the whole simplex. So that's barycentric coordinates in a nutshell, right? Now, OK, in the case where x happens to lie within the triangle, then it turns out that the sign of the determinant will always be positive, because if it was negative, then these ratios will just cancel out, and so you'll still get a positive number. Except in the case where if we took a different choice of x, right, and let it lie, say, somewhere out here. So pick another x. So we'll still have this triangle here, p0, p1, and x, right? But the determinant of this can now be a negative value, because it's now the opposite sign of the interior triangle. So it's now oriented in the wrong way, right? Now, this would sort of violate this convexity constraint, which I've erased, unfortunately. But it still is a reasonable thing, right? So I will now draw a separate picture here to kind of illustrate this. So imagine if you just take, say, a pair of points, P0, and another point, P1, and then they determine a line, right, as we saw in the last class, right? Now, if I take a point here, x, and I look at this triangle, right? So imagine this ray goes off over there to infinity. I have this angle theta. All right. So the determinant of the matrix, P0, 1, P1, 1, x1, tells us whether this point x lies above this line, below the line, or on the line. Or another way to think of this is that if we imagine that we take this triangle and assign an orientation to it, then we're going to say this quantity, which we're going to call orient, of P0, P1, and x, and that's equal to the sign of the determinant here, right? This has three separate meanings, right? Or there's three possible outcomes for it. So the first is greater than 0, which implies counterclockwise in a right-handed coordinate system, equals 0, which implies that all points are collinear, and less than 0, which implies it's clockwise. So if we have some tuple of 3 points in the plane, we can assign this orientation to them. And in general, if we take a simplex determined by d plus 1 points in affine d-dimensional space, then we can assign an orientation to that tuple of points. So one way to interpret this is that you take the first d of the points in that tuple. You can imagine that it's generating this line here. And this line is basically cutting the entire affine plane into 3 components. The components which are above the plane, the components which are on the plane, and the components which are below the plane. And this leads us to our next idea, which is the concept of a half space. All right, so I'm going to erase this idea here, right? OK. So here's the concept of a half space. All right, so all right. Now I'm going to make sure I introduce this in the right order. OK, so the basic idea is we'll start, instead of from a point in affine space, we're going to start from any hyperplane, right? So any d minus 1 dimensional hyperplane. So we'll say, given a d minus 1 dimensional hyperplane, which would be a line in 2D or a plane in 3D. We're going to call it H, contained in d-dimensional affine space. H partitions AD into 3 parts. All right, so here's kind of the picture, right? This is H, and we'll say we have this part up here, which we're going to call, like, say, the positive part of H. We'll have this part here, which is the negative part, and we have the parts directly on H, which are 0, right? So imagine that we just take affine space, the whole plane, we cut it into these 3 different points. So how does this work, right? Well, we can define it explicitly in terms of coordinates. So let's suppose that H is determined by a normal vector, right? We'll call this n, right? As we saw, this was one way that we could define a point or a plane, right? Plus, like, some offset to the, a coordinate system or a coordinate origin. So we'll say that this is O. So this length here, we'll call this C, right? So we can imagine that there is some sort of function, which we'll write as basically h of x, that's going to be equal to n hat dot x plus d, right? So that's basically this vector offset. So these three components correspond to h of x greater than 0, h of x equals 0. So this level set, let me write this here. So we'll say h plus is equal to the collection of all x such that h of x is greater than 0, such that h of x is equal to 0. Collection of all x such that h of x is less than 0. All right, so these are the three ways that we can do this. And as we've seen, that given a tuple of d points, right, because they determine a plane, as we saw last time, right, then we can also construct a hyperplane, using this orientation operator. So the idea would be that we just leave this last variable here, x, open, right? We don't fix it, and then just fix the parameters p0, p1, p2, et cetera, for the points that determine the plane, right? And now we can just plug in that last x, and then it tells us above, below, on, all right? So now, OK, suppose we're given some tuple of points, right, in 3D or 2D, and we'd like to solve for the coefficients of this plane. All right, well, again, we can just use Cramer's rule to do that. In higher dimensions, it becomes kind of messy, but in 3D, there's a sort of nice geometric interpretation for it, because we have sort of a situation where we're going to feed in two vectors, right, in order to construct the sweep of this structure, and then we're going to get basically a third vector out, right? So we imagine if we subtract off the first row, p0, right, in order to go kill that, right, then in 3D, we'll basically say orient p0, p1, p2, and then this is just an open, unbound variable, right, is a hyperplane, right? And is a hyperplane. We'll say this is just basically a hyperplane space, and hat dot x plus d, right? Where if we solve for this n hat, what we'll see is that it's going to be equal to p1 minus p0 cross product with p2 minus p0. All right, and the definition of this is that it's basically just these minor determinants expanded out. So what we'll get is basically the notation here gets a little bit weird. So we'll just call this vector here, we'll call that guy A, call this vector B. This is going to be the determinant of AY, BY, AZ, BZ minus AX, BX, AZ, BZ. Just applying Cramer's rule, really. There's not much else to this, but yeah. AY, BY. All right. So this is essentially where cross products come from. And this only really happens to work in 3D because once you get to higher dimensions, you run out of points that you can kind of plug into this. So it doesn't really have any particular meaning in that sort of sense. But one of your homeworks is also this problem of converting sort of points that are represented in this sort of primal form into points that are represented in this sort of hyperplane dual form. OK, so that's the concept of a half space, right? And also the concept of a simplex. All right, but we're not going to be happy with just simplices. And so now we're going to come to actually the main subject of this first part of the course, which is convex polytopes. So, and we already kind of seen the very beginning of convex polytopes through simplices, right? In fact, simplices are an instance of a convex polytope, but the idea itself is more general. And one of the kind of problems with working with just simplices is that while they are sort of nice and easy to do calculations with, they're not algebraically very well behaved. So if you take the intersection of two simplices, it's not a simplex. If you take a projection of a simplex, again, not really a simplex, right? And so in some sense, if you just take simplices as a whole, and you just want them to be closed under projections or like affine transformations, then what you will end up with are convex polytopes. And so this is actually how a convex polytope is defined, right? Which is that it's some set which happens to be closed under convex combinations. So I'll start out by saying what a convex set is, right? And then I'll say more specifically what a convex polytope is. So we'll say S contained in AD is convex if for all P0, P1, these are just pairs of points in S, the line swept out by P0, P1 is contained in S. Right? So we'll basically say that the set T, P0 plus 1 minus T, P1, T in the interval 0, 1, is contained in S. Right? So this is the definition. Right? So simplices are convex. Half spaces are convex. Actually, flats are convex. So far, everything we've seen has been convex, right? But convex sets also include things which aren't in this space, right? So for example, like the intersection of two simplices, right? Might not be a simplex, but it would be convex, right? So to say a couple of quick things, right? So here are some basic properties. How am I doing for time? I forgot to check this. Oh, yeah, tons of time. OK. So here are the properties, right? Well, actually, I'm not going to bother to prove these. They're really easy to check, though, right? So the first part is one, affine maps. And this includes projections, not just transformations, right? So if you take a convex set and squish it to a lower dimensional convex set, right, of convex sets are convex, right? So here's kind of like a picture of like a convex set. So you can imagine I have some crazy looking thing like this. And if I project it onto a line, all right, then the resulting line is also convex, right? So I can take any projection of a convex set, remains convex. Two, intersections of convex sets are convex. So these are kind of two separate properties. So the idea would be, imagine I have like a convex potato here, another one here. I intersect them. The resulting lens or whatever is going to be convex. OK? So that's easy. You're also closed under some more interesting operations. For example, the Cartesian product of two convex sets is convex. So we'll say the Cartesian product right, so this would be kind of the idea. Imagine if I have like an interval here, a Cartesian product at something like this, then the resulting square that I would get is going to be convex again, right? And the sort of the kind of mental proof is that, well, I can just take the line segment here and the line segment here, and then the Cartesian product of those segments will remain convex, right? So also pretty easy to check. Some of these may show up as homework problems, perhaps. So what?
What is the Cartesian product?
Right. So if you have Cartesian product, so the idea is if you have two sets, S cross T, then it's basically the set of pairs, right, where you have S in S, T in T. That's it. Right. So you basically take S and T, and you form the set of all pairs of points. So if you have like two affine flats, right, one in d-dimensional space, the other one in n-dimensional space, Cartesian product them together, you get one in n plus d-dimensional space, right? So that's the Cartesian product. And then finally, they're also closed under Minkowski sum, right? of convex sets. In some sense, the Minkowski sum is kind of like the opposite of intersection in a dual sense, which we will not fully explain until a later lecture because we're not going to talk about duality in convex sets today, but we will get to it soon. So, OK, the Minkowski sum of convex sets is convex. This is a little harder to see, right? But you can imagine if I have some like box here, and I Minkowski sum it with a ball, then the resulting thing will look kind of like I offset it by a ball, right? And everyone remembers what the Minkowski sum was from last time, or people who are just joining us for their benefit. I will write out the definition here very quickly, right? So the Minkowski sum of two sets S and T is this set of sums, right? So this is only defined, of course, if they're in a vector space, but we'll come back to this in a moment, or at a later time. Right? So the Minkowski sum of S and T, S and S, T and T. Right? So you can think of this as just the set of all sums of the points. Right? This only works, again, if they're in a vector space, right? But we can define convexity for vector spaces. It doesn't have to be restricted just to affine space. OK. So those are the basic kind of properties of convex sets, just like lightning overview. So like lots of basic algebraic stuff still works. That's OK. Now, all right. Most operations that we're going to do in this class will basically reduce down to various properties of convex sets, right? So a lot of like things like point location in planes, or finding sort of like intersections between areas, or checking for collisions between objects will all kind of reduce to different queries on convex sets or operations on convex sets. So we're going to need to think carefully about how we want to represent these convex sets on a computer. And it turns out that, as in the case of flats, there are basically two different ways we can encode the data in a convex set. All right, so I'm now going to first explain probably the most familiar one, right, which is the concept of a vertex polytope, or V-polytope. All right? So we'll give you the two definitions, right? And then we'll talk about how they're related, right? So here's the first way that we can represent them, right? So this is, so far we've just seen convex sets as an abstract mathematical structure, but without anything that you can like plug it into a computer and start crunching numbers with. So the first representation is a V-polytope, right? So here's the basic data that you need. So I'll say, given a finite set V, so it's just some collection of points in affine space, we'll say a set P contained in affine space is a V-polytope if and only if P is equal to the convex hull of these vertices, or these points, right? OK, so this is just a point set, right? They don't have to. The vertex will soon come to mean a very precise thing in a moment. So that's a V-polytope. This is sort of the one of the most common representations of a polytope, right, or of a convex set. Now, there is another representation, which is, in a sense, precisely dual to this representation. This is called an H-polytope. And perhaps you can already guess how this is going to work based on the last time, right? But this is, just the sort of parallel version of, affine subspaces, right? And so an H-polytope is formed by an intersection of half spaces, all right? So we'll say, given a finite set of half spaces, and we'll write these guys as basically H sub I equal to H And then D, we'll say that P is an H-polytope if P is equal to the intersection of each of these HIs and H. Okay, so these are the two parallel forms that we have for representing polytopes, right? And they lead to two parallel concepts. So here's kind of the first picture of a V-polytope. So imagine I take a bunch of vertices, splat them down on the plane. I'll use red for this. So I have these vertices here. Then their convex hull is the set of all of these convex combinations. So I can imagine I take this point, and then for every other point, I'll sweep out these lines. You know, I just fill in this whole region here, right? So from a V-polytope, you can see that there might be these redundant vertices that would be contained on the interior of V, right? Are these redundant points? I don't mean to say vertex, right? So in the same way that we could say, given an affine space, we could find sort of a minimal basis for generating that affine space, such that if you pulled out even one of them, it reduced the dimension or it changed that affine space into a smaller one. We could talk about a minimal generating set for a V-polytope. And these are called the vertices, right? So vertices. The vertices of a V-polytope P are the smallest V such that P equals convex hull V. So in other words, if I take, there could be any number of points here in like this generating set, but the only ones that matter are the ones that are on the very boundary. So if I took out this point, it wouldn't change the convex hull of these points. So these extreme points here are the vertices, right? Similarly, for an H-polytope, there is a dual concept, which are the facets, or they're sometimes called supporting hyperplanes in like optimization literature. So if I take a collection of half spaces, so we'll say like let me get out another pen. Come on. Let's try this. Right, there we go. So imagine this is one half space. Take another half space here. A whole bunch of them. Then the intersection of all these half spaces, right, will form some polytope. And so the facets right, basically the minimal I'll try this one again. It's working. Minimal set of hyperplanes. Right, so I can imagine that maybe there's like another hyperplane out here, but it doesn't do anything. So the ones that actually matter are just these hyperplanes here that generate the shape. Okay?
How exactly is minimal set like? Just so it's this
You can think of it as if I removed even one of these hyperplanes, then the resulting intersection wouldn't be P. So we'll think of it as the minimal set of hyperplanes H, or capital H, such that P is equal to the intersection of all HI in H, right? So you can think of this as like, well, this is basically like, just says that there has to exist some H, but if you take the smallest possible set of H, right, then you're going to get the facets of this polytope, right? And that's true for H-polytopes, and these are V-polytopes. Now, You're probably thinking it would be nice to have some sort of duality between these two things. Sorry, yeah?
Yeah, so how do you uniquely define the area that's contained in which facets?
So each of these facets, right, is basically a hyperplane, right? So each of these HIs, they're a half space. They're not a hyperplane, right? They're a half space. I should probably be a little more precise there. But OK, a half space is basically like this closed area, right? So we'll think of this half space as basically the collection of all h of x less than or equal to 0, right? So by some abusive notation, you can imagine that this is sort of like a row vector, right? So I'm feeding in an x, and then it's going to tell me like some scalar value that'll pop out of it, right? And so if I take all of these guys, which are, say, less than or equal to 0, right, or greater than or equal to 0, it wouldn't matter, whichever one, that cuts out this half space here, right? So if I take a bunch of these half spaces, I intersect them all together, then the resulting shape is going to be convex, right? Because each of these half spaces itself was convex. And so because the intersection of convex sets is, again, convex, I will end up with some convex set. That convex set is called an H-polytope, right? That's just what they're defined to be. And given any H-polytope, there is some minimal set of hyperplanes, which turns out to be unique, right? But we're not going to prove that right now. But just take my word that it's unique, all right? That will basically determine that set H, or that polytope. That minimal set of hyperplanes are the facets. In exactly the same way that if I take a set of vertices, or a set of points in the plane, then their convex hull determines this this V-polytope. The minimal set of these V's, the minimal set of vertices or points, right, are the vertices of the convex polytope, right? So we have V-polytopes and we have H-polytopes. We have vertices, we have facets, right? This one is formed by intersections. This one is formed by convex combinations, all right? So what we would like to have is some kind of duality between these two things. So these are the two main ways that we have on a computer, that we can like digitally or numerically represent polytopes. And much of the work in computational geometry and really in algorithms is just converting from one representation to another. And so if we wanted to do this, we would like to first say that these representations are equivalent in expressive power. And indeed, it seems obvious that if you take a V-polytope, that you could write it as an intersection of H-polytopes. And we'll come to this in a moment and prove it. So if I take just these lines on the boundary here, then I could just rewrite this whole thing as an intersection of these bounding facets, right, of this V-polytope. So this particular V-polytope is also an H-polytope. But are all H-polytopes V-polytopes? Does anyone take a guess?
Can't you just put points on all the intersections of the half spaces?
Yeah, in this example, I definitely could. But maybe there are examples where this wouldn't work. Can someone think of one? Exactly. Right. So here is one where this would fail. If I took, say, two half spaces like this and intersect them together, well, the resulting H-polytope will basically be this whole region going off to infinity. And in affine space, there's no way I can stick points at infinity. So it seems that there's no way I could go from an H-polytope to a V-polytope. So for now, we're going to just accept that we can kind of not do that, or we're not going to worry about that part of the problem. But we can definitely go from V-polytopes to H-polytopes. And that's what we're going to do now. And there is a name for this problem. It's called the convex hull problem. All right. Right. So, but first, let's actually prove that this is a well-defined thing, that you can actually go from V-polytopes to H-polytopes, because definitely the opposite isn't true, right? Like in affine space, anyway. So, all right, I'm going to erase all this now. All right, so here's the first real theorem of the day. I think I'm going to do that. And it has an algorithm in it, but we'll see that it's a hilarious algorithm and that you would never actually want to do it. But this is a constructive proof, all right? And it will work in any dimension, and it will be terrible. But we're going to do it. All right, so here's the theorem. Every V-polytope P contained d-dimensional space is an H-polytope in AD. All right. So this is the kind of fundamental theorem of convex polytopes in affine space, right? It's not perfect. The projective one is better, but we're going to do that later. All right. So here's the first observation, right? So if we recall the definition, right, of a V-polytope, then this guy is going to be, basically this A0, P0 plus, et cetera, plus A, D, or we'll say that we have n points, right? AN, PN, such that 0 is less than or equal to AI, and A0 plus AN equals 1. Right? Well, this whole mess here, right, is actually an H-polytope, but it's just in a higher dimensional space, right, like a crazy large one. So we'll basically say every P like this is secretly an H-polytope. And this H-polytope P prime, secretly an H-polytope in, we'll just write it in, say, we'll work in real coordinates for now, right? Being a little bit sloppy, but put it in RD plus 1, or RD plus n. I should start from 1 here in order to make my indices correct. OK, P prime, where it's basically the collection of all these, x a's, in RD plus n, where we have this equation that x is going to be equal to a1, p1, et cetera, plus an, pn. We have an inequality for each of these AIs. And then we also have this constraint that all these guys have to sum to 1. So that's kind of obvious and somewhat trivial. So if this was true, though, right? This is obviously true. So given this point of view, right, all that we would really need to do in order to turn a V-polytope into an H-polytope is just project this whole thing onto the x component, the first d variables, right? So if we can just show that given an H-polytope, if we can project that H-polytope onto a lower dimensional subspace, and the resulting thing is still an H-polytope, then we would basically show that this theorem would hold, right? So all we need to do in order to prove this is to just figure out how to do a projection onto a lower dimensional subspace, or just kill a variable in an H-polytope. So here's sort of like the picture, right, of what's going on. So I have some crazy H-polytope up here. I want to show that if I project this crazy H-polytope onto a line, the resulting projection is still an H-polytope, right? So it's not that it's convex. Obviously, the projection will be convex, right? We know that. But it's more than that it's convex. I need it to be an H-polytope. This thing has to be expressible as an intersection of half spaces. OK? All right. So how do we do this? Well, this will be our first algorithm in the course. And it's called Fourier-Motzkin elimination. And this is actually like the most insane convex hull algorithm ever invented, because it was invented like 100 years ago before they had computers. And so it's extremely inefficient, right? But it does work, right? And it's kind of beautiful in a way of its own sort of like brutality, right? Like it just is like a very scary algorithm in a way because it's so simple and the complexities involved are so large. So, all right, so what Fourier-Motzkin elimination does is it basically computes projections of systems of linear equations, or inequations, right? So if you have like systems of linear half spaces, it will basically project them onto lower dimensional sets, right? So to do this, it actually suffices, first of all, to just say how to project onto a single variable, right? So we'll start explaining this. And the name for this is because it was invented by Fourier, who did a bunch of other stuff, right? But definitely existed in an era before computers. elimination. And basically, this just it's an algorithm for projecting away variables in systems of linear inequalities. All right, that's the high-level idea. All right, so we're going to basically say, okay, so here's our input. Right, so the input is basically a system of n variables. Right, so we're not even going to worry about the polytope thing. This is a more general kind of idea. Right, so it is basically a system of let's say n variables, x1, x2, etc., up to xn, all sitting in Rn, and m inequalities. All right. So I won't write what the inequalities are, but I'll say just one simple observation. So here's the trick that makes this work, right? So the first observation there are three types of inequalities, right? So, all right, well, actually, before I do that, let me go say one thing. I should say what our goal is, right? So the goal for now is to find equivalent system such that there exists, xn, right, satisfying the previous constraints, right? Satisfying new inequalities. So basically, we just want to kill the variable xn, right? So we're going to basically start from the system of n variables, m inequalities. We'll construct some new system of inequalities, which will be the same as the projection of all of the solutions of this system down to just the first n minus 1 variables. So it's just going to kill one variable. That's all we're going to do, right? So to do this, here's the goal, or here's the trick. I'm going to erase this side here because we'll need some space. So here's the trick. Three cases for each inequality. And because they're linear inequalities, this is, how we will break it down, right? So the first case is 1. We'll call these guys A-type. Which is that we'll say, OK, there's some parameter bi minus these constraints, mi sub k for k equal 1 to n minus 1 times xk is less than or equal to xn. Right? So this is basically the first type of inequality. The second type of inequality, we'll call these guys B-type. Again, we'll say these guys such that minus k equal 1 and minus 1. K, or use j as the letter here. Xk is greater than or equal to xn. And then 3, whatever, independent. All right, so these are just equations that, we'll just say that these are basically constraints like C sub L, which no xn variable, right? So these are basically the three different cases, all right? Now, as a notational trick, or as a notational convenience, we're going to introduce some auxiliary variables here. So we'll call this guy A, I, and this will just be a functional of the previous x's, right? We'll set that equal to here on the right side, on the left side. Here we'll set this b sub j, follow those variables. That's going to be equal to that part, and so on.
Is the I from 1 to m for the inequalities, or is it?
Yeah, I from 1 to there. I reuse the variable m. Just think of this as like we're going to enumerate through all of the different inequalities, right? So for every one of these m inequalities, we can classify it into one of these 3 types. All right, so we're going to have the ones where basically if I rearrange all of the terms so that xn is on the right-hand side of our greater than or less than symbol, if it ends up, when I just cancel off the leading terms using division and whatever and just push it all the way over there, that I'll basically have the xn by itself here, right? So you can think of this as like if you've ever done like Gaussian elimination by hand, or if you have like a system of polynomial equations and you're trying to solve them. This is kind of like the trick. So you just pick a variable, you try to figure out all the places where the variable is by itself, and then you just solve for just that one variable, and then you can substitute it back into the equation and then keep working, right? Here we have inequalities, so it becomes a little bit nastier, right? But the same basic idea holds. So what we'll do is we'll say for each of our inequalities, we're going to have, we're just going to rearrange all the terms so that the variable we're trying to get rid of, this x sub n, is on the one side of the equation, and then the rest of the junk is all over here, right? So we'll just say, OK, just separate the variables out in each constraint so that it's just on a side by itself. And when we're all done with that, there are 3 possibilities, right? Either this thing will become a less than or equal to, it'll be a greater than or equal to, or it just doesn't have an xn in it, so we can ignore that one, right? So now from these constraints, what we want to do is we want to basically kill off these a and b constraints, right? These are the ones that have something to do with xn. So we're going to have to get rid of them and replace them with something else. And we can just leave these c constraints alone because they don't have anything to do with them. So here's the idea, is that now we're going to build a new system, right? And the key observation here is if I look at all these AIs and BIs, right, I could rewrite all of these constraints using a min-max operator. So the basic idea is the system is equivalent to taking the max of all of the AIs, right? So we'll say A1, whatever, A2, etc., up to like, I don't know, however many A constraints there are, right? It's going to be less than or equal to xn. This will be less than or equal to the min of all the B constraints. So I can take all of the A constraints and all the B constraints, and I can create a new nonlinear constraint, which is the max of all of these guys and the min of all of these guys. So if I wanted to eliminate x, right, well, all I have to do is just do that, right? And now this is an equivalent system that doesn't have our xn in it anymore. So this kills the variable xn, and now we're left with a new equivalent system of constraints. Except it's nonlinear. We have a max here and a min here. But there's an easy way to get rid of that, which is we can just do this for every pair, right? So we'll basically add, so say that there are NA constraints here. Say that there are NB constraints here. So we'll just say add NA times NB constraints. We'll basically say AI less than or equal to B sub j for all AI, for all ij, right? So just enforce every possible pairwise constraint. And now we have a new system of equations, which now has basically quadratically many extra constraints, right? And we've killed one variable. So if you iterate this n times, the complexity, right, of doing this becomes order n to the 2n, right? Which is pretty bad, like worse than order 2 to the n. It's insane, right? But it will work, right? And more importantly, this also gives us a means to convert a V-polytope and an H-polytope or calculate a convex hull, right? So this is the first algorithm for convex hull calculations, all right, that we have seen. And we have also proven, as a side effect, that V-polytopes and H-polytopes are the same. OK, great. So yeah, that took a little longer than I thought, but we'll get to some actual stuff now. So all right, that's the basic properties of convex polytopes. And so the first set of algorithms that I want to talk about, and I'm probably not going to get too far today, is the problem of computing the convex hull for a planar point set. And we'll see a number of algorithms which are much more efficient than this Fourier-Motzkin technique, right? And they'll get pretty fast overall. But let's just point out, a couple of properties of what would actually. Well, let's see. I only have like 6 minutes here, so. OK, so this is what we're going to talk about next time. We're not going to get to it today. So next time, 2D convex hulls. This is sort of the warm-up for moving on to higher dimensional convex hulls, which we'll see you can calculate all kinds of things if you can do convex hulls very efficiently, right? The basic problem is to compute the facets of a V-polytope. In the plane, right? So that's the idea. And we've already seen that you could use Fourier-Motzkin elimination to do it. You probably don't want to, right? But there are other ways to do this, right? To illustrate this, though, here's a very simple brute force algorithm, right? I'm just going to sketch out how this would work. And we'll see much faster ways to do it than this, too. So this will get like really, really fast. But imagine if I take any pair of points, call these guys pi, p sub j, then I could just test all other points against this line using that orientation test that we talked about at the start of the lecture, right? And in this way, if I just iterate through every pair of points and then test every other point in the convex hull again, or in the point set against that, then I can very quickly, just enumerate all of them. So that would be a sort of simple cubic time algorithm. So obvious upper bound it's basically order of n cubed, right, where n is the number of points. I will say one word now about the lower bound, right? So there is a lower bound, which is pretty far from this, right? And we'll get to the lower bound. So if I take a set of arbitrary points in 2D, right, and I lift them up, or kind of project them down onto some structure by basically squaring them. So we'll say this is like, say, x0, x1, x2, x3, x4, etc. Take a line. Then I can write, say, like x0, x0 squared, x1, x1 squared, etc. Then the convex hull of this set of squares of these points, these lifted points, or they're kind of pushed down, right, is going to contain every one of these points. And moreover, if I construct this hull, this is actually going to give me the points in sorted order, right? So the lower bound is proportional to the complexity of sorting all of the points. So the lower bound here would be order n log n, all right? So, or omega n log n, all right? So this is in the worst case lower bound. So you can construct a point set where it would definitely take n log n time to compute a convex hull. There's a lot of room in the middle, though, right? And so we'll see some different approaches to this in class tomorrow. But I believe that today's lecture is done. So I think we're just going to have to stop here. OK, that's it.